Okay, let's get right into this explainer and unlock the hidden behavior of the instruments we rely on literally every single day. Whether you're working on your diploma, training to be a tech, or just stepping into the industrial world, understanding how your tools actually behave is absolutely step one. So, let's kick things off with a slightly provocative question. Does your measuring equipment ever just straight up lie to you? Like when you look at a digital readout and it says exactly 100 degrees, can you blindly trust that number? Well, the short answer is, it's complicated. Every piece of hardware out there has physical limitations, and today we're going to decode exactly what those are.
To figure out if we can actually trust our readings, we're going to break things down into these 5 key areas. We'll basically split the world of measurement right down the middle, starting with the static characteristics of an instrument, and then switching gears to the dynamic characteristics.
All right, Section 1, Intro to Instrument Performance. We are starting off in the still world.
Here's the most crucial thing to wrap your head around. We have to evaluate instruments in 2 completely different worlds. First, there's the static world, where conditions are unvarying. Nothing is changing. Think of this like snapping a quick, still photograph. But then you have the dynamic world, where the process is rapidly changing with time. That's more like shooting a high-speed video. You really need to know how your gear acts in both scenarios.
Now, before we can even think about trusting a static reading, we've got to calibrate the instrument using these 4 logical steps. First up, you examine its construction and list out all the possible inputs. Next, decide which of those inputs actually matter for your specific setup. Then, you get the right apparatus to vary those ranges. And finally, you hold some inputs constant, vary the rest, and record the output against a known, trusted standard.
Moving right along to Section 2, Understanding Static Characteristics. We're going to tackle 2 words that pretty much everyone mixes up when they first start out.
First is accuracy. Accuracy is all about the truth. As the definition points out, it's how close your instrument actually gets to the real-world value under reference conditions. Basically, if the temperature in the room is strictly 100 degrees, a perfectly accurate thermometer is going to tell you it's exactly 100 degrees.
Precision, on the other hand, that is all about exactness and repeatability. It's the consistency the instrument was designed to have, completely regardless of whether it's actually hitting the true target.
And this comparison brilliantly clears it up. You can have an instrument that is incredibly precise, meaning it gives you the exact same answer every single time, without actually being accurate. It's just consistently wrong. For real-world industrial processes, you absolutely need both, but it's super important to realize they are completely separate traits.
Okay, Section 3. Time to meet the villains that love to ruin our static readings. Static errors.
These errors basically fall into 3 buckets. First, you've got your standard human mistakes, literally just misreading a dial or writing down the wrong number. Second are systematic errors. These act as a constant bias, kind of like a stretched spring or a super hot room that consistently skews your data. And finally, random errors. These are just caused by unknown chance, and honestly, the only way we can manage them is by using probability and statistics.
One of the most fascinating systematic errors is called the dead zone. This is the largest range of values where the actual process changes, but your instrument just stubbornly sits there and ignores it. This dead spot is super common, and it's usually just caused by simple mechanical friction inside the indicating parts. It basically ghosts you.
We also have to be on high alert for drift. Drift is this incredibly sneaky problem in industrial environments because you almost never notice it right away. It's caused by wear and tear, corrosion, stuff like that, and it gradually shifts your calibration over time. Think of it like your smartphone battery slowly losing its maximum capacity over a couple of years. It might be a zero drift, shifting everything by a flat amount, or a span drift, changing proportionally across the scale. You've got to catch this stuff with continuous inspections.
The legendary physicist Lord Kelvin once said that knowing your numbers is power. But that knowledge is honestly pretty useless until you understand the sources of your errors. Recognizing these static characteristics isn't just textbook theory. It's a non-negotiable skill for anyone entering the field.
All right, moving into Section 4. We are flipping the script and diving into dynamic characteristics. We're leaving that still photograph behind and entering the moving world, where variables are fluctuating super fast.
So here is the harsh reality check. Out in the field, instruments are sluggish. They literally cannot respond to a sudden change instantly. And the reason is pure physics. They have mass, thermal capacitance, or fluid capacitance. Because they are physical objects in the real world, they just need time to react to the energy transferring around them. Which brings us to the concept of dead time lag. When we map this out, you'll see a specific gap, a peer delay, labeled T. During this time, the instrument is essentially just waiting for a physical reaction to happen. The process itself is already changed, but during this dead time, the needle hasn't even started to twitch yet. When we evaluate dynamic instruments, we grade them on these 4 main traits. We want a high speed of response, meaning it reacts rapidly. We want high fidelity, so it faithfully follows changes without distorting the signal. But we actively want to minimize lag, that annoying delay we just talked about, and dynamic error, which is the actual gap between reality and what the delayed dial is showing you.
And that brings us to our final stop, Section 5, measuring the dynamic response. How do we actually test this sluggishness in a lab setting?
To see how an instrument handles the stress of moving variables, engineers basically torture test the primary elements with 3 artificial changes. A step change, which is an instant, finite jump, a linear change, which just steadily ramps up over time, and a sinusoidal change, which forces the instrument to follow constant wave patterns to check for things like resonance.
We can neatly categorize their mathematical behavior using this cheat sheet. Zero-order systems are basically the dream. They follow inputs perfectly with zero distortion. First-order systems introduce a time constant, meaning their response drags behind on an exponential curve. And then second-order systems are the most complex. They add physics like natural frequency and damping, meaning they might actually bounce or oscillate before they settle down.
Let's think about how this plays out visually. Imagine hitting a first-order system, like a standard glass thermometer, with an instant temperature jump. A huge step change. The fluid doesn't just teleport to the new temp. It traces a smooth, exponential curve over time just to catch up to reality, which is defined by its characteristic time constant. But throw that exact same instant jump at a second-order system, like a fluid manometer, and you get a totally different vibe. Depending on its damping ratio, the needle might wildly overshoot the true value, bounce back and forth a few times, and only eventually settle on the actual truth. Which leaves us with one incredibly critical thought to end on. If we know, as a hard fact of physics, that our tools are subject to these static errors, dead zones, and dynamic lags, what kind of absolute disasters might happen if we just blindly trust the dials in a high-stakes, automated environment? Understanding this stuff isn't just passing a test, it is literally the difference between a tightly controlled process and a catastrophic failure. Thanks for joining me on this Explain Up. Keep asking questions and never stop analyzing your tools.